This video is going to deal with these two topics. Okay, I can utilize the molar heat of fusion and vaporization to calculate energy change due to phase change. And then I can also calculate the energy change for any substance that goes along the heating curve, meaning not only do you have a phase change, you might also have a temperature change. The equation for this was presented in class already. Q equals delta H times mole. So that's the equation I'm going to be using in order to calculate these problems. Problems look like this. Calculate the heat of vaporization for 55.0 grams of ethanol. My plan for this video is really to show you one problem of each of the two types that were presented for the learning targets. One where you just calculate energy and one where you have a phase change and a temperature change. So here's your first one. Calculate the heat of vaporization for 55.0 grams of ethanol. And I give you the chemical formula of ethanol. On the test, that's something that you should know. Since this does not have a temperature change, I know I have to use the Q equals delta H times mole. Okay. The heat of vaporization for ethanol can be found on your thermochemical reference table. Vaporization is actually one of the ones listed, so you just have to pull the number right off of that. Okay. So the delta H for vaporization for ethanol as listed is 38.7 kilojoules per mole. Now this problem gives you 55.0 grams of ethanol, and in this equation you need mole, which is not a problem. You see grams, you see mole, you think molar mass, so we're going to go grams to mole of ethanol. The molar mass of ethanol, if you add it up, is 46.069, which gives me a mole amount of 1.19 mole. Then you solve it. 38.7 times 1.19 is 46.2, and that's in kilojoules because your delta H is in kilojoules. So if you take this unit and multiply by mole, the mole will go away and all you'll have left is kilojoules in the end. 46.2 kilojoules of energy is absorbed because it's positive, and we know that it's absorbed also because you need to take energy in to increase the space within the ethanol to vaporize it. So those problems aren't very complicated. It's just a question of recognizing that there is no temperature change and identifying the correct heat to use, vaporization or fusion, knowing that vaporization is also condensation if you make it negative, and fusion is also solidification if you make it negative. So here's a second problem type. And if you read it, it looks just like a Q equals MC delta T problem we've had before. I have a mass, I have a change in temp, I get my C from my thermochemical reference table, and I can calculate the energy. The problem is if you read it and if you look at that temperature change, for water, you cross over a phase change within this temperature change region. What that means is if you look at this heating curve, you're starting on one part of the slope, you're crossing over the flat part, and then you're actually increasing on the slope again. What that means is in order to calculate the energy required to heat up, change phase, and heat up again, you need to do three separate problems. Okay? Basically, you take your substance and quantify how much energy it takes to get it to 100, how much energy it takes to make it from liquid to steam, and then how much energy it takes to heat it up from there to the 117. The reason you have to do it in multiple steps is all about the specific heat capacity. When you're in liquid water opposed to steam, your C will be different. So you could quantify the amount of energy it takes to heat up this water all the way from the starting to the ending. But what C would you use? Because within that range, your water is both liquid and gas. You got to split it up and make sure you're only dealing with one state of matter for each of your temperature change problems. So going back to this problem, 150 grams of water heating up from 35 to 117, I'll show you how I would set that up. Because I'm going from some temperature of liquid to some temperature of gas, you can see how I have three separate Q's to quantify. This is to heat it up from 35 to 100. This is to go from a liquid to a gas. And then this is to go from 100 to 117. I'm using 100 here because that is my boiling point. Right here where I'm not changing temperature anymore is at 100. So essentially I have three separate problems Once I can quantify the Q required for each of these individual components, I would just add them together. So I set up my problems like this so that I'm very defined in terms of what I'm doing. I'm heating up to 100, I'm changing the phase, and I'm heating up again. Each of these corresponds to a different branch on that heat phase diagram to know what I'm doing. For change in temp, I use the Q equals MC delta T calculation. For this, I use the Q equals delta H times mole for a phase change. And for this, I use Q equals MC delta T. So the challenging part for your phase change component is number one, choosing the right C, and number two, defining the correct temperature change. Our initial temperature for our substance is 35 degrees Celsius when we're in the liquid. Okay? We're in the liquid range for this problem. The temperature final then, when you're in the liquid, is 100. You can't have a liquid water above 100. That's your capping point. The C for liquid water is 4.18 joules per gram degree Celsius. Once we've made it into a gas, our initial temperature now that it's at is 100. We're no longer at 35 because you can't have an initial temp of 35 for gas water. It has to be over 100. And then the final temp that we're going to end at is 117. Now in terms of sig figs, you don't really use this 100 as part of your sig fig measurement since that's something you determined. Okay, don't have that limit you. The C then you choose is the C for water vapor, for the gas. Okay, and you have your thermochemical reference table to look at in order to determine that value. So if you plug in your defined variables into your Q equals MC delta T problem, the amount of energy required to heat up to 100 is right here, 3 sig figs. The amount of energy required to get it to 117 from 100 is right here, 3 sig figs. Between those two is a phase change, and the phase change requires a delta H and a mole amount. The delta H will be the delta H for going from liquid to gas, which is the delta H of vaporization. Again, you have your thermochemical reference table to look at to determine what that value should be, but it's 40.7. And that's in kilojoules per mole. The mole amount, I don't give you a mole amount, but I give you a gram amount, right? Same as before. If I have grams and I need mole, you see grams, you see mole, you think molar mass. And that'll get you to mole amounts for that amount of water. That's just a question of plugging in and solving. Something to remember for this problem type though, that Q will be in kilojoules because your delta H is kilojoules per mole. The final step is to add all the energies together because this is the energy to heat it up, change a phase, and heat it up some more. But joules, kilojoules, joules, that's not okay. They need to all be in the same unit for you to add them together. What I usually do is I change my kilojoules to joules by moving the decimal point over 3 spaces. Now I can add these together, and your final answer will all be in one measurement. If I add that plus that plus that, I get this. And that's your final answer. That's an example of each problem. Go ahead and do the form, and have a nice night.